Hi, I'm Takahiro Sumi from Osaka University, representing the Prime team. I'm going to talk about the status of the Prime telescope. So the Prime is the Prime Focus Infrared Microlensing experiment. The primary is the 1.8 meter. We have a 1.45 scale degree field of view. This is the 6 times of the full moon, and mostly observing the H-band. This is the first dedicated near-infrared microlensing survey. And we are going to support the Roman mission by conducting the precursor observation and also the concurrent observation. So here is the hardware contribution by the Prime partners. Osaka University's Astrobiology Center built a 1.8 meter telescope. And as for the near-infrared images called the PrimeCam, the Osaka funded and Roman chain loaned the 4H4RG near-infrared detectors, and the University of Maryland, they manufactured the camera at the Goddard Space Flight Center. And the Astrobiology Center is currently building the near-infrared spectrogram, and Osaka will build the zone, and also the SAO will build the building. So here is the PrimeCam. This camera was manufactured by the University of Maryland, led by the Alex Kamkushin at the Goddard Space Flight Center, loaning the 4K by 4K H1G detectors loaned from the Roman team. So here is the focal plane, and inside of the camera there's a 2 field of view. As I said, the field of view is 1.45 scale degree. The running temperature is 170 K, and using the Arcadia electronics, which is the same as the Roman. And here is the comparison of our field of view compared to the other major infrared telescope like Vista, Roman, and the Yukon. So as you can see, the Prime is one of the widest field of view telescope in the near infrared. So we have 2 field of view. So each filter have filter 1 have the YJH, and the filter 2 have a dark Z and narrowband filter. The limiting magnitude is about 21 in Z, 20 in Y, and 19.4 in J, and 18.5 in H band with 100-second exposure. And the narrowband filter, the 3 narrowbands are imprinted in the 1 filters, and we can select each one of the narrowband by combining with the other wideband filter. So the objective of the Prime is as follows. 50% of the telescope time are spent for the microlensing exoplanet search towards the galactic bulge. This is specifically for studying the Roman Prime outside of the snow line, and also measuring the frequency of the planets in the galactic center that can be compared to the frequency of the planet outer region of the galactic bulge measured by the optical survey. And we are also optimizing the Roman microlensing survey field by making the event rate map in the galactic central regions. And after lunch, we are conducting the concurrent observation with Roman to measure the lens mass. And other 50% during the home season are shared by the partners institution. 40% by SAO, 20% by Osaka, NASA, and ABC. So each institution conducts any survey for science of their interest. And especially many institutions are interested in the TOO observation for the transient, like a gravitational wave, high-Z GRB, supernovae, Galileo or TDE or something like this. And ABC, they are building the near-infrared high-resolution spectrogram. They're trying to do the radial velocity search for the habitable planet around the ambient stars. So any idea is very welcome for collaboration. So after launch of the Roman, we are trying to do the simultaneous observation with the Romans. If we observe the same event from the ground and space, because of the different line of sight, we measure the different light curves, different peak and magnification and the timing. This is so-called the space microlensing parallax. By measuring this, we can measure the mass and distance of the lenses. So that was demonstrated by the ground-based and the speed synergy observations. And Prime and Roman can do the same things. And this is the only way to measure the mass of the free-floating planets. And especially the distance between the Earth and the L2 is best suitable for searching for this small Einstein radius by the free-floating planets. So after the delay of the construction by the COVID-19, we finally completed the building, dome, and the telescope in July 2022. And then we installed the camera PrimeCam in October 2022. Then after several issues are resolved, we started observation in July 2023. So this is the team from Osaka and the NASA to installing the telescope at the site. So this is the image of the H-band at the first right, Jupiter, Sutherland, and the craters of the moon. So we have a very excellent quality. So we are there are many troubles in the camera, telescope, and dome, and solving each time. And then last year, we have a major upgrade of the dome. The issue of the dome was the gears of the dome rotator. We are out only every 6 months. And the dome rotates very slowly. Our telescope moves very fast, but it takes time to dome catching up the telescope. And then it's not smooth because we didn't have an inverter. And slits misalign to the telescope sometimes. So we decided to replace our old motors, 4 new bigger motors with inverters, and also we added 6 position center. And then now the dome moves very fast and smooth and very accurate. We are very ready for observing whatever, the fast transient as well. But just after this upgrade, we had a failure of the dome slit. This slit was stuck half open. We cannot close and open at all. So and also this is very high position. We couldn't access to this motor position, and then we don't know what's going on. So we flew the drone to take a movie around this, and then we found it, the coupler between the motor and the gear here was loosened. So we built this scaffold to access to the dome, and then we tightened this coupler. It took 2 weeks to recover this one. So this is kind of the side effect of the COVID. Because of the COVID, the actual engineer from the dome company couldn't visit here when we are building the dome. So, but fortunately, we could recover this. Now it's working very fine now. So here's the observational field of the prime. This color map indicates the event rate map by the oval observed by the optical. And this magenta is the observational field by the Moore collaboration. And this purple indicating the one example observational field for the Roman. And this blue square is the main survey region by the prime. This is the 35 fields, 51 scale degrees. We are observing this region with the cadence of the 2 hours 20 minutes at the beginning, but we changed the strategy lately to increase the cadence of the 1 hour 10 minutes by reducing the exposure time. And we are also observing this light blue region. for lower cadence. This is for the measuring the infrared source magnitude for the observation by the more collaboration. So here is the example images. Now we are getting the 4 chips working properly. This is the region of the candidate Raman field. You can see we are observing many stars in this region. Here is another example images near the galactic center. The Sagittae is somewhere around. We have still significant extinction, but we are still observing many stars here. Here is a pie of the observational field. Here is the center of the galaxy, galactic plane. We are seeing more closer than the optical survey. So the data reduction is very challenging. Data rates of the prime is 120 terabytes per year. We are currently storing the data in the server on site and then transferring to Osaka by the internet. But it's sometimes delaying, so we use the hard drive to catching up the transformations. So we are keep improving the pipeline iteratively, but it's mostly it's good shape, doing the nonlinearity correction, dark fits, flat fielding. The Ryusei Hamada is going to detail, talking about detail. And the difference imaging pipeline is developed by the Ian Bond. He will show you the detail later. So here is the example, the before the difference imaging, then this is the after the difference imaging. So we are already detecting the many variable stars and the microlensing events. Here is the example. The nice ESF shape was detected on the difference image here. And this is the light curves from the half the season. The blue point is the photometry from the each exposure. It's a 10-second exposure. And the red is a stack of the 6 exposure in one visit. So you can see the short period variable. Here is the other long period variable. You can see the nice light curves. So here is the example microlensing. Here the detected on the difference image, and you can see the nice microlensing shape. Here is another good microlensing light curve. And this is the apparent binary events. Here is the cosine crossing here. So we are planning to the upgrade of the camera windows. Currently, we are using the dry air to avoid the condensation, but we're planning to replace it to sapphire window after the ceremony. This is needed for the remote observation, so then we don't have to, replacing the desiccant every day. And we will gradually shift to the remote observation. So here's the summary. We started Galactic Bulge survey in the July 2023, and we upgraded Dawn last year, and currently developing the pipeline and detecting the variable stars at microlensing. And we'll upgrade the Sapphire camera window to shift to the remote observation. Thank you.
Okay, any questions for Taka? Marcus was first up on that.
Hi, Taka, thanks very much. I was just wondering, at some point you've mentioned we'd like to install active optics, but I suppose given for the answer to Valeria's question, this was not envisaged, or was it?
Sorry,
the installation of active optics.
Active optics. Oh, I don't know what's the other active optics. We don't have any such idea.
I think you wrote me at some point that you wanted to have actuators on the mirror in order to get the shape automatically adjusted.
No.
Okay, then I'm no problem.
Oh, the one of the lens is active. Yes. That is only for the calibration purpose, not the real time.
So the narrowband filters are designed to block OH emission and give you a much lower background. But there could be some issue with the, it's very independent of the angle of the light. You have images, so they never been images that you can show and see whether. Low range vision.
I don't have any the images right now, but we took some images to be reduced very soon. But I think that the effect is I think negligible compared to the width of the narrow. I mean, in the effect of the instant angle, right?
I don't know.
I think so.
We have time for one more quick question. I saw him first, I'm sorry.
It's a good question. So for collaboration, does collaboration include the possible idea of looking at fields you're not currently looking at?
Yes, yes. So the our bulge system we can observe anywhere. So if you have any good idea and propose us, then we can collaborate for look at anywhere.
Great.